Professor Versace is the co-founder and CEO of Neurala, the founding director of the Boston University Neuromorphics Lab, and in the course of his career, he collected numerous degrees and recognitions from renowned universities and institutions. Versace worked with the DARPA, with the NASA, the National Science Foundation, and other agencies to develop a one-of-a-kind AI able to run on any device. And today, millions of devices worldwide are powered by this very AI. So let's see if he's already with us. Good morning, Professor Versace. Can you hear me?
Good morning. Yes, I can.
Okay, well, thanks for being with us. How are you doing?
Very well, very well. Thanks for having me. This is my first digital, trade show, so looking forward.
The first digital keynote. Well, I know that you're about to share with us some secrets about AI and some applications of AI, but maybe before that, you would like to introduce to us your company, Neurala, and its activities?
Absolutely, yes. So the company was started actually as a spin-off from Boston University in 2006. Me and my colleagues, Ed and Anatoly, we started it essentially as a science experiment, and pretty much it became our life after that. So we, as you mentioned, we worked with NASA, DARPA, National Science Foundation for a few years until NASA actually gave us enough money to take the company out of the lab and become from a 3-people shop, about 50 people today. So the company specialized at the beginning in autonomous robotics, and over time we have found a product market fit, and we have landed on machines that are a little bit bigger than a Mars rover, but much more useful on Earth and widespread, which are industrial machines. And so today we are deploying our AI, which is in about 56 million devices today. We're looking at making it more powerful and useful for industrial use cases, among which manufacturing.
Okay, thank you very much. Well, now we all can't wait to see and hear what you are telling us about artificial intelligence. So, Dr. Versace, please.
Thank you. So we are going to talk about artificial intelligence, and the typical image that people have, when I evoke the name artificial intelligence is these sort of things, right? So the incarnation, the embodiment of AI are, for reasons that have to do more with Hollywood than with reality, they usually evoke the idea of humanoid robots or other sorts of robots, even improbable bodies like kangaroo robots or snake robots or humanoid, dog-shaped robots, dinosaurs, and so forth. In reality, thankfully, AI is very, very different from that, right? So this is just a snapshot that portrays a global AI software market that, it hovers around $120 billion by 2025, that encompass many different disciplines and many different embodiments of this AI. So not only robotics, which is actually a very tiny minority, but we go from the A of agriculture all the way to the software development tools, cybersecurity, ad techs, legal, finance, healthcare. It has a huge amount of application, retail. And then there are companies like ourselves in the corner of platforms that are building, in fact, platforms or tools that can be used by companies to build and deploy artificial intelligence in tasks such as visual inspection. So it's very, very broad and has very little to do with the humanoid robot and Terminator, if you will. So what about manufacturing? So AI manufacturing, as you can imagine, has huge applications. And so, aside from these, sterile, almost sterile numbers that portrays, from 1 billion to 17 billion CAGR of, market size with an increase of, roughly 50% per year, the majority of this new wave of artificial intelligence that is coming to manufacturing is actually deep learning. And we will be talking what deep learning means and how it matters for manufacturing in a second. So deep learning is spearheading the revolution of AI into manufacturing. And The subset of deep learning that counts for manufacturing is actually the one that exists on device or on premise, right? So it's true that the cloud is going to envelop everything in our life, but when it comes to manufacturing with the very specific requirements, it's on premise that dominates. It doesn't matter if it's in 2018 or 2027. So huge opportunity among which deep learning is spearheading, and this deep learning is going to be on device or on premise. So the world has obviously taken a twist in the past few months, but it didn't really change anything about the march of AI into manufacturing. If anything, it has accelerated it and made it more urgent and useful. So the pressure is on for manufacturing to rely less on multiple humans. So what we want is the ability for many, so from less people to be able to manage more and more machines. Increase efficiency, productivity, reduce waste, optimize machine, and ensure the ability to flexibly change a production line. So the answer to these pressures is obviously more AI and more automation. So that's the main combo that will assure manufacturing to meet the requirements above, right? So what is this artificial intelligence? So I was, as mentioned before, I was a scientist for many years. And among many other thousands of scientists around the world, our job was to decode the brain, right? So study the biological brain, write down equations that describe the functioning, the physiology and the anatomy of its components, neurons and their networks, of which we have about 100 billion neurons in the brain with 500 trillion synapses. And then once you build this system, you connect them together to emulate behavior, then you have something useful that you can implement in a practical application. So AI is a discipline that is fairly old, and there's been a kind of a switch between the so-called good old-fashioned AI, or GoFi, which was the dominant paradigm until roughly 2012, and neural networks, which are the real word for the so-called deep learning algorithms. So AI has been around for many years, and a way in which we can think of the difference between good old-fashioned AI and neural networks is by looking at a toy example. So imagine that you're building an AI to distinguish between an apple and an orange. So a traditional algorithm, which looks like a decision trees that you see here on the left, will go something like, is the thing that you're looking at a fruit? If it is a fruit, is that roundish? If it's green or orange, then you might navigate different branches, different leaves, and end up in either the apple or the orange. And so that's how a traditional AI algorithm roughly would work. So this is dramatically different from neural networks. So you see the diagram on the right. That depicts a typical deep neural network that, as opposed to having these very explicit decision trees defined in it, the way that it works is you present images, you present examples, many of them, of what an apple and an orange is. And within those networks, within those synaptic ways that are the links uniting neurons with each other, the learning algorithms inside those synapses will help the network self-organize and decide autonomously which one is an apple and which one is an orange. So these are data-driven algorithms. So the key here is to have data to expose the network with, and then the network organizes itself and decides which one of the two objects you're looking at. And intuitively, we all know how our brain works. So that's an example of my last two creations. Obviously, my wife did all the work, but this is Leonardo, the small one, on the right, and Aria, who just turned 3, actually on the right, and Leonardo on the left. So they do not have decision trees in their head, right? So they completely self-organize their neurons, mostly by practice, mostly by exposure to a huge amount of data, which is our reality. And this network tune themselves. There is no explicit way in which a parent can install a decision trees in the brain. So we all know that intuitively this is how it works. And finally, the world has caught up with this intuition. So initially in academia, around the 2010, 2012, many of the competitions that are used in order to benchmark one algorithm against the other started to be won by this neural network or deep learning algorithms, starting from object recognition to written language, to traffic sign, medical imaging. All these competitions were won by deep learning algorithms starting in those years. And the real world followed, right? So what initially is done in academia very soon becomes a standard also in our industrial settings, for instance, or in our consumers' machines. And just my little company, Neurala, as mentioned before, we have put our AI at work in about 56 million devices worldwide, spanning from robots to drones to smart devices or cell phones, as you see in a second, all the way now to industrial machines. So let me give you a few examples of what this means out of, this is just not theory, but it's some stuff that every one of you already has sometimes in their pockets. So that's one example of implementation of AI that we have done in the past couple of years. So we are deployed in tens of millions of cell phones. And every time you take a picture with this smartphone, that we cannot disclose the brand, but it's a top 3 brand. Every time you take a picture, AI inside the phone that we have designed segments the image you're seeing here, trees or animals or plants that are immediately segmented as soon as you take a picture. So what does this do to the customer? Essentially what you have is the ability to have an expert photographer in your pocket, right? So I'm not an expert photographer, and many of us are not. The AI in the phone helps each picture become stunning. So you increase the quality of the picture, you build a better phone, and of course the manufacturer has the advantage of selling a phone that is fantastic for customer to take picture with. Everything is done with a piece of software running on the cell phone. So let's move to robots. So this is a robot that is deployed in about 600 grocery stores in US. It's called Marty the Robot, and the robot essentially is a restless worker that goes up and down the aisles, performs several tasks. In one of these tasks, for instance, as you can see here on the insert on the right, the robot is able to detect whether there are spills in grocery stores. So these are tasks that you don't necessarily want the human to do. You want humans to do more complex things, and so you can offset part of the dull and repetitive jobs to robots that goes up and down incessantly on the aisle and alerts the personnel if there has been a spill on the ground, and of course does many other things along the way. So let's go to flying robots. In this case, it's a drone. We are deployed in both US and Europe in infrastructure monitoring. So an operator usually flies a drone and takes pictures or videos of infrastructure, right? So wind turbines are an example, or in the screen on the right you can see electrical infrastructure. So these infrastructure need to be inspected constantly to prevent downturn and other things to happen. Usually, how these inspections are done is by sending a human on top of a wind turbine, which is neither fun nor necessary anymore because you can fly a drone. So once you fly a drone, you detect terabytes of images, and the problem of going through these images to understand where the defect is present is another cumbersome task. And so AI screens through this gigantic amount and pinpoints to you have a damage on this piece of infrastructure. So eventually they can send somebody up to fix the damage. So these are examples outside of manufacturing. So what about manufacturing? How does AI help streamline our industrial machines and production settings? So it's not obviously unknown that there is a problem in manufacturing, right? So there is a huge talent shortage, at least in US, but we believe that this is more generalized than just US. 80% of manufacturing companies are willing to pay more than the market rates in workforce area, really under talent crisis. So there is a shortage of workers, and traditional machine vision or traditional way to automate processes is not the answer for this problem, right? It's not sufficient. And so you're starting to see machine vision and artificial intelligence acquisition and moves in the market to start to take this technology and put it to work to face these labor shortages. And AI is already widely applied in a few use cases already. So machine vision is used already in quality inspections. For instance, in component presence, can be used for both packaging machines and assembly kitted, and it can be used to check if the expected items are in the box. Labor inspection, so these are logistic cases where we already are working heavily, both in Asia and in Europe. So this is about flexible, personalized custom packagings, and the inspection process needs to adapt quickly. So AI can take either the place of humans or supplement the work of humans in these use cases. And the other one is pallet inspection. Of course, with so much shipping going on, at least in these days, I don't go to the grocery store anymore. I get everything shipped to my house. And we need to ensure that the pallet is built correctly and the pallet has arrived in good condition and detect defects and so forth. So AI can help streamline this process also in these logistic use cases where the same issues of the scarcity of workforce and more intermittent workforce is already present. Though when we say deep learning, it's not a miracle technology, right? So deep learning comes into different forms and shapes, and it also has its own shortcoming. So let's look at a practical example of how, for instance, a bottle producing facility might use deep learning in their use cases. So imagine that we want to build a deep learning model to streamline quality inspection on bottle caps. And as you know, bottle caps can come into all sorts of different shapes and forms. And this is the typical workflow that a deep learning implementation has to go through. So the first step is to collect thousands of images of caps, right? So for each type of cap, you need to collect images of all possible anomalies that can occur, right? So you can have one particular type of bottle cap, and then you need to collect all sorts of variation errors that particular bottle cap can have in order to be able to catch them after you build your network. So the very key important things to consider here is that you need to, in a traditional deep learning needs to have so-called balanced data set. What this means is that you need as many examples of good images as you have of bad images for your data set. So if you have 1,000 images of a good cap, you need to have roughly the same number of bad cap or damaged caps. Then once you have that, once you have your data prepared, you need to train your network. It can be minutes, but more typically would be hours or even days if your data set is gigantic. And once you've done steps 1 through 4, then you're ready to take your deep neural network and deploy it in an application. And if you have to change it, you have to go back to step 1, 2, 3, and 4. So it's not a simple process, and it takes time and expertise to do. But the biggest issue, as I was mentioning, is the imbalance between the number of normal and the anomalous images that you have. So thankfully, a production facility is designed such that to minimize the number of bad things that happen to products that you're building. And so the idea of an unbalanced data set is actually, that's more of a rule rather than an exception in manufacturing. So that's the problem. That's the one of the major obstacles in fielding deep learning algorithm inside manufacturing use cases. So that's where the brain comes to the rescue, right? So our brains are able to detect even the tiniest anomaly based just on example of good images, right? So I don't know if you guys have had the chance to look at the real Mona Lisa. I wasn't, because there were 3,000 tourists in front of me, but you've seen the portrait at least in prints many times. And so if I show you a version on the right that has a very tiny anomaly, and here we are talking about pixels, right? Just a few pixels around the corner of the mouth, you will be able to spot it seamlessly and very, very quickly. So the brain, our brains, is designed to learn over time and constantly every day what normal is, and catch very quickly whether something that violates the normal or your usual perception has happened. And so what we have done throughout our work with DARPA, NASA, and so forth is design algorithms that mimic this very property that our cerebral cortex has developed over our biological evolution. And so we are able to do that in software today. So how does that work in a production facility? So it's very simple. All you do is, as a human does, you just need to expose example of what a normal bottle cap is. So you show, let's say, 20 images of normal bottle caps, and then you're basically ready to deploy your AI. That's it. You just show normal, you just show the canonical bottle cap, and then if something that violates these canonical bubble caps, which is the equivalent of the few pixels around the corner of the Mona Lisa, if those are off, then your AI is going to start to develop an anomaly or send a signal out to the operator and say, well, something is wrong here. And so what if you're changing your production line and all of a sudden you're introducing a different kind of cap? Well, you do the same. You present a few tens of images of what normal is. In this case, it's a blue cap. And then you're ready to deploy your AI, and if there is a deviation, your AI will alert you that something is going astray. And very importantly, this takes minutes. It's not something that you need to either have expertise in doing or set up for half an hour or several days. You just present a few normal cases, and then you're good to go. So we are good friends with Ima, and I'm going to show you here a couple of examples on how this AI reduced to practice can be applied in a manufacturing context. So I'll show you initially an example of a visual quality inspection, and I will run a video here, and I shut up for a second and listen to somebody else speaking English better than I do. I hope you can hear the audio.
No, we cannot hear the audio right now.
Oh, you can't hear the audio. Okay,
nope.
So unfortunately you have to listen to me. All right, so that's an example of an anomaly recognition for visual quality inspection
and easily using our platform.
Now it works.
What?
Okay, oops. Let me go back. Sorry for that.
Yeah, let's restart.
What you're seeing is building a model to identify defects on a bottle cap inspection line quickly and easily using our platform, Brain Builder. Simply upload a minimum of 20 acceptable and any defective images that you have, if available, and let our patented AI do the hard work. Set a region of interest to remove confusing background information from what the model actually learns. Then, evaluate the performance with relevant metrics, moving to a test deployment scenario in minutes rather than days. You just saw end-to-end building a custom model to automate visual inspections in seconds, making it easier for you to move to 100% visually inspected product line.
So that's an example of our technology, the things that we started to develop for Mars rover, down to a piece of software that can be used by anybody to automate quality inspection. So the technology under the hood is really complicated, but the process from the user is actually extraordinarily simple. It's as easy as, or actually easier than use a Photoshop software. So all you need to do is to trace something on the screen and tell it this is a good product. That's it. And so everything else is done by the AI under the hood in minutes without having you to know what AI is, what deep learning is, or having to tune any parameters like you should do if you're using traditional machine vision. So that's an example in visual quality inspection that we are fielding today with a few of our customers. So the question here spontaneously arrived, well, this seems too good to be true. Well, in reality, it is kind of, right? So it's a piece of software. It's designed just to be installed in your current infrastructure. So you most likely have already what you need in your site. So an industrial PC, an industrial network, gig camera, no need for special hardware. So everything is in place. It's just a software plugin that you might just be able to put to work again in a few minutes. So this is the example above was about visual quality inspection. What about non-visual application of AI? So a typical machine is a very complex beast that has many, many different sensors, out of which camera are just a small subset. So what about beyond vision? One of the things that AI can be used for is to reduce unexpected downtime, leveraging data coming from other sensors other than 2D cameras. And so in 2016, a survey uncovered that about the unplanned downtime event cost for a typical machine ranges about 260,000 per hour and lasted 4 hours. So there are huge wastes that are a consequence of a machine downtime. So can you harvest from existing data, most of which are not visual, inside a machine and put AI to the service of the machine itself, trying to reduce this unexpected downtime? And it's more about being strategic about when the machine is taken out of service rather than anything else. So let me show you a typical example of what this can be achieved in a coffee pressing machine. This is a coffee capsule machine. Has plenty of sensors, and the sensor here in the video check the quality of the seal applied to each machine cycle. So you see here in the graphics a phase and power spectrum that essentially takes the sensor information displayed on the screen. So what you can do is the equivalent of what we have seen in the quality control inspection case before. In this case, the data is not an image, but it's a 1D sensor data stream. And you can take these and feed it to an AI algorithm. So you do the same exact thing that we did before. So we just run the machine and say, this is normal, right? So the Mona Lisa example, this is a typical example of what normal is. And then you just learn for a few machine cycle and deploy your AI. And so if later an anomaly comes out, which can come into many different forms, right? We didn't know that the anomaly in the Mona Lisa was at the corner of the eye, it could be the mouth, it could have been in any other part of the painting. When this anomaly comes out, then our AI alerts the operator that something unusual is happening with respect to what a typical functioning cycle was learned before. So this is fundamental. This is a huge improvement in what the typical condition of this machine is. And you can take this action immediately based on this information to improve sealing quality. And maintenance then can be planned rather than unexpected. So we're working on this with some of our partners, including, of course, IMA. So all that I show you today is coming. We hope in 2020 is the year we're going to see this technology applied at scale. So after 56 million devices, not in industrial machine, we're going to start to see this technology trickle into our production facility. So this AI would be simple, right? So that's the difference with respect to traditional machine vision, which has been present for many years in manufacturing. This would be extremely simple. You won't need an expert, and you will not need special equipment or special cameras or special sensors to be applied. All you need is an industrial PC connected with a standard camera. It will be responsive. It will enable flexibility with existing machines, right? You can retrofit, since it's so easy to install as a piece of software, you can retrofit existing machines as well. And it will be dynamic. So you will be able to configure and reconfigure as many times as you want per day, and and augment and tweak your AI as your production evolves throughout the day. So we all know we are in a situation of a crisis, but as the great Winston Churchill reminded us once, never let a good crisis go to waste. So we are obviously under pressure, but this is the time to accelerate adoption and deployment of AI, because that's exactly what we need today. So AI augmented manufacturing is here to stay, and a technology that we were looking at for tomorrow has become today now and fast. So we are eager to work with IMA and our partners to make this technology successful and useful for industrial manufacturing. Thank you, and happy to take any questions.
Thank you very much, Professor. Thank you so much for dedicating some of your precious time to us and for sharing your very, very interesting visions on artificial intelligence. Well, we're running out of time, so unfortunately we don't have time to ask you the questions coming from our viewers, but maybe we will send them to you via email after this live session. So thank you very much and greetings to Boston.